Okay, so our next speaker is Adrian Thob, who will be talking about synthetic survey catalogs for the Galactic Roman Infrared Plane Survey.
Okay, thank you very much. Thanks for the organizers to allowing me to talk about our work. Today I'm going to speak about our efforts that we're doing to produce Galactic Infrared Plane Survey. I'm a postdoc at University of Pennsylvania working with Robin Sanderson. And what I want to start with is just reiterating on what Chitsuke was mentioning earlier during her review, is that this work is a sort of side project of a larger effort that the RINGS Wide Field Science Program is taking to produce pipeline and data sets that would prepare us for Roman's ability to get star surveys in nearby galaxies. There is certainly a common interest between the rings, but also the Galactic Plane Survey, in that sort of common enemy that is the effect of crowding. We have actually, as part of RINGS, already a pipeline that we've been developing, which the objective is to be able to benchmark photometry routines that would be able to reduce photometry from Raman images. And one of the tools that we're using for creating a Galactic Plane Survey is the PyNNK tool that we developed in an effort to adapt the NNK software that Robin developed back in 2020. What NNK was this work where she produced mock surveys of Gaia DR2 of the Milky Way using cosmological simulations. In this case, it was the Latte suite of Paris simulations, where we had 3 different volumes that were simulating Milky Way-like galaxies in high resolution. What we improved upon from NNK is the fact that NNK was made out of individual Python and C++ routines, which made it really hard to integrate within the RIGS pipeline. We improved upon this to create a single streamlined plug-and-play Python package, which is available online and for use by anyone. But on top of that, where NNK was actually dedicated to produce Gaia photometry, now we've actually added more different photometric systems. On top of it, the modular implementation of it that we have with PyNNK make it easier for further upgrade, notably in post-processing. In more detail about what NNK does is that, as I mentioned, it's using as input cosmological simulation data that is in the form of star particles. Each star particles come with position, velocity, masses, and various physical property. What NNK does is to wrap around the Galaxia software, which in this case is modified to be able to use, instead of the Besenson model, using actually the simulation data as the Galaxy model. It will actually use the various star particles input to first sample the phase space out of density estimations, and also the IMF out of the mass of each star particles, and to produce a first catalog of synthetic stars. And in second steps, we'll actually interpolate out of the synthetic stars to get the photometry, the synthetic photometry, using preloaded isochrones. So depending on the photometric system that has been used, that has been given to it, we get then a mock catalog that has photometry and astrometry, but is just very ideal without any extinction. With all of this in post-processing, in the case of the Galactic Plane Survey that I'm about to show you, we actually have an extinction driver that takes into account the gas content from the simulation, where for each star particle, we get an estimation of the line of sight column density, dust column density, assuming a ratio of dust to metallicity ratio. On this, then we get actually the synthetic survey. I just show actually above here a little snippet of code to show how simple that entire process comes. When it comes in Python, it's just a couple of lines and just carefully use keyword arguments. So to create our Galactic Plane Survey, what we do is use actually the specifications from Roberta's white paper, where they actually suggested the different galactic coordinates to limit the survey to, but also the sensitivity that Roman will have access to. one advantage of PyNK is that we can give it a limit in terms of like a mask in terms of the column-height diagram to produce. That allows us to actually avoid creating a large amount of very low mass stars that would produce a huge amount of data that would be unnecessary. So in this case, in pre-processing, we define one specific magnitude limit in the F158 filters, and we do the rest in post-processing. That does mean that out of PyNK, the actual survey we do get is a full sky survey. We do eventually limit to the galactic plane after in post-processing. We also include Gaia DR2 and LSST photometry because we wanted to compare the difference between having only near infrared bands in Raman, but also the showing the difference between the capacity of Gaia DR2 and what LSST will have access to. So here on the left, it doesn't show very well on the screen. On the left, you have actually the full sky survey that results out of the PyNK run in flux maps. So on the top, you have the Gaia DR2 flux maps, and in the bottom, the Raman. I'm talking about a prototype 2% survey. This is 2 terabytes of data. This is still a work in progress. Getting to actually a full 100% coverage would create 100 terabytes data. We're still working on this. But here we already have 2.4 billion stars to work with, and you can already see on the flux maps the ability that Raman will have to be able to dig into the dust clouds and really see what's behind, which Gaia and LSST wouldn't be able to see. On the right, you have column-height diagrams using extincted and reddened absolute magnitudes. So those are actually the output of PyNK, but just removing the distance modulus. And the heat maps that you see are actually here the galactic plane specified reduced surveys. So we are actually using the disk and plane. And we show in the heat maps only the stars that are being detected by each instrument. On top, you have the numbers of stars of source detected. We have between 20 and 25 million stars in the optical bands of LSST and Gaia, when Raman will be able to see 670 million. And to illustrate that further, you can see actually the extent in the column magnitude diagram that is shown by the contour plots on the 2 left diagrams. These contours represent what would the heat map cover in terms of the column magnitude diagram space if we were to include all of the source that Raman detects, but the 2 others don't. We wanted to understand a bit further what those stars that are being detected only run Raman are. So here we're looking at column magnitude diagrams using unextincted and unreddened absolute magnitude this time to look at their physical characteristics. On the top, what we're looking at are the stars that are detected by both Raman and as well as Gaia or LSST. In the bottom, those are the Raman only detection. And what is very visible and what we would assume is that, of course, Raman will be seeing a large amount of red faint dwarf stars, which is characterized by this massive blob at the bottom of the column magnitude diagrams. But nonetheless, we do actually still have a nice continuity in the main sequence and the asymptotic branch, a giant branch, that is very similar with the top panel. And those are probably stars that are actually hidden by the dust clouds and that Raman will be able to see. So as I mentioned, this is still a work in progress. The current catalog is 2 terabytes. What's available is actually the photometry in Gaia DR2, LSST, and Raman bands, as well as various astrometry, including proper motions as well. And each of the stars come with the properties that are carried from the simulation itself, such as age and chemical abundances. We have a little bit more work to do. Notably, the very important aspect that we need to work on is this ability to be able to do 100% coverage simulation. For this, we need to actually improve the optimization of our pipeline. Since the pipeline right now is single-threaded, it takes about half a day to produce this 2% prototype survey. If we're able to parallelize this a bit further, we would be able to potentially have this actually be integrated in pipeline on the go and create simulations on the go. Another aspect that I'm particularly interested in would be to expand on more surveys, not just using one simulation in one observer position, potentially having different simulation to imagine different configuration possible, but also different observer positions would allow us to test, for example, if we imagine a survey on the rim of a spiral arm or in between two spiral arms. So thank you very much for your attention, and I'm open to any questions.
Thanks, Adrian. We have questions. Okay.
Yeah, okay. So great work. I was wondering if the catalog is available to be seen somewhere.
Not yet, but we can definitely chat, and
All right.
we intend to make it available.
Okay, thank you. So just a point of clarification for me, the philosophy of this is not to produce as close a realization of the Milky Way as possible. It's to put in a cosmological simulation. So we shouldn't be using these models to optimize placement of fields.
Sorry?
We shouldn't use these models to optimally place small numbers of fields, for example, in the microscopic surveys.
I'm not sure. Do you mean like the fact that it's not the Milky Way itself?
Yeah.
Yeah, indeed. It's really like in this case, really for ourselves, what we want to do is being able to study the effect of crowding.
So you said it takes about a half day to do a 2% survey on one core. Is there any reason you couldn't just kind of split it into different regions that are not overlapping and then run that, on 10 cores or 20 cores and then stitch them together at the end? That maybe would be cheaper for now than, doing a real multi-threading?
So that's actually indeed a strategy that I'm going to right now. I've been trying a couple of things, and there's some limitations that I've been seeing, that notably Python, essentially. Parallelizing Python is a little bit of a nightmare sometimes. So that's actually the strategy I'm considering for the further works.
Any other questions?
Hi, thanks for the awesome talk. I guess I was wondering, do you, sorry if I missed it, but do you just include the objects that would be in Galaxia, or do you also include, would you include compact objects or binaries? And how would you plan to add those if you don't have them in yet?
So yeah, this is one of the limitation also. We did not actually have any way with the current pipeline to produce population of stars that would be self-gravitationally bound, such as global clusters or binary. This is something that we are in discussion with Jitsuke, and we would like to potentially have a way to actually also produce global clusters in the pipeline, but this is not available yet, and there's some work that needs to be done on this.
Thanks.
Thank you for the question.
Okay. Any last questions? We have time for maybe one more question. Okay. Is that a yes? Okay, here.
So sorry, you mentioned that this is obviously, not quite the simulation or representative of Milky Way, but then why do you carry both the age and the, chemical abundance information? Do you see what I mean? Because one of my questions was going to be, before you gave that response, was, oh, hey, have you tried to recover what's, already present in literature? But that's not the point, right? So I'm just curious why you, also report that information.
So the pipeline doesn't have, the PyNK itself doesn't have only a purpose. We don't want it to be only for this project. We want it to be more broadly to be used by some other aspect. There's always this sort of question about when we have hydro simulations, how to compare them with observations. There's certainly sort of like ping pong between simulation and observation to try to refine the simulation models so that the simulation is more realistic. The reason why we carry over those parameters is so that we can actually do that work potentially in the future of being able to refine the simulation model out of the actual observations. So it's sort of future proofing.
Okay, let's thank Adrian again.